Well, this is the third presentation of 12 on the structure and properties of organic molecules. In the first, we looked at how to understand skeletal drawings or skeletal structures or representations seen in most books or articles covering organic chemistry. There's going to be some picture of a molecule using skeletal representation. And in the presentation on drawing structures, it was learned that kinks or carbons, and an end here has 3 hydrogens off of a carbon, or a CH3 group. The wedge signifying that that group is out and above the plane of the paper, and the dash signifying that it's below the plane of the paper. And these 4 atoms, the sulfur carbon and the 2 carbons here, are at tetrahedral orientation to each other. So these are just practical things that are necessary to know as you look at drawings that organic chemists use to talk about their work. The second recording started to make an advance into, or I guess dive into, the atomic structure of atoms within the skeletal drawing. And we learned that electrons around a nucleus take certain shapes, certain orbitals which have certain energies, and we married the concept of orbitals with what was known from the lab through Linus Pauling's work on hybridization, so that the simple structure of CH4, methane, could be explained by an orbital theory. So knowing that in the lab it was known that these bonds were equal and they were tetrahedral to each other, the CH bonds in CH4, and this was bridged or explained by Linus Pauling using hybridization theory, wherein mixing of the 2s and the 3 2p orbitals to give 4 hybrid orbitals that are at tetrahedral orientation, and that would give equal bonding to each of the 4 hydrogens in CH4. So this was a very, very groundbreaking work by Pauling to marry what was known in lab with what was developing in the 1930s regarding electrons as having both particle and wave properties. This recording, the third of 12, is looking at how to use hybridization theory not only to set hybridizations of nitrogens, oxygens, and carbons primarily, but how we can, through that hybridization, see the orbital picture of the molecule. So let's make an advance on application of hybridization theory. It's interesting as we go into setting hybridization and seeing orbitals through it, to remember that much can be done, even though there are particular wave functions that electrons around a nucleus has to be in, or this quantized view, particular energies of particular orbitals of 4 electrons around a nucleus. It's interesting, this confinement, but there's much freedom to create and to make a wonderful world within pharmaceuticals, materials, even within this constraint of this confinement to S's and P's and D orbitals. Let's look at what we're going to do for the next 5 to 10 minutes is look at 3 different structures wherein we have 2 carbons bonded to each other. The first will be in a single bond, 2 carbons in a single bond. The next will be ethene or ethylene, where we have carbon in a double bond. And then the last one will be ethylene, where we have carbon in a triple bond. We'll be looking at how we can set hybridization for those carbons and how we can see the orbital picture for those 3 structures. So let's start with our first one, the simplest one, ethane, where we have a single bond between the carbons. What is the hybridization of the 2 carbons in ethane? Well, we can have an understanding of the hybridization we need by knowing that single bonds have to be sigma bonds. Sigma bonds are the strongest bonds. So if you're going to make a bond between 2 atoms as they start to come together, you're going to have head-to-head overlap of orbitals. That's just sigma bonding. It's stronger than pi bonding. So we need, if we're going to have 4 single bonds, we need sigma bonds, and these sigma bonds are made when it comes to carbons, nitrogens, and oxygens. All sigma bonds are made through hybrid orbitals. So you can kind of do a logical extension. If single bonds, then sigma bonds, then 4 hybrid orbitals are needed. So we can say, since these have 4 single bonds off of each carbon, 1, 2, 3, 4, 1, 2, 3, 4, these single bonds have to be sigma bonds, and we need 4 hybrid orbitals, because every sigma bond has to be made using a hybrid orbital. So the only way we can have that is to have all 2s, 2s and all 2p's ground together to make 4 hybrid orbitals, sp3. We have to have 4 hybrid orbitals. We need to put the 2s in with the 3 p's. That would give us, and we know it's in the name, sp3 hybridization. We have 4 hybrid orbitals. That gives us the hybrid orbitals we need to make those 4 sigma bonds. And here's the orbital picture. We know from the last presentation that we have tetrahedral orientation of the 4 hybrid orbitals, the 4 sp3 hybrid orbitals off this sp3 carbon. These in green are hybrid orbitals that are being used to bond to the hydrogen. This one in pink is just denoted as such because it's going to be bonding to the hybrid orbital, the sp3 hybrid orbital of the other carbon. So this is sort of an incomplete valence bond description of the structure of ethane, where we've left just the hydrogens out, but we've shown this sigma bond between the 2 carbons. There's our first structure. Let's look at the 2 others. Ethylene, or it's also called as ethene. Ethylene or ethene. And let's start just with the skeletal structure, I guess, or Lewis structure. Either one we can use as a start to set hybridization and see orbitals behind the structure. So let's just take note that these hydrogens along with this carbon are shown in the plane of the paper. Along with these 2 hydrogens are shown in the plane of the paper. These bonds are not wedges or dashes. So that's something to note. So this would be a planar structure as far as the atoms go. And as far as the hybridization, we can set that 2 different ways. We can remember that all single bonds have to be made using hybrid orbitals. So we have 1 single bond, another single bond, and you say, well, what do you do with the double bond? It's not double of one type. One bond is a sigma bond, head to head, and the other is a pi bond. So a double bond is always a mixture of a sigma and a pi, and we'll see triple bonds have to be a sigma and 2 pi's. You can only have 1 sigma bond between 2 atoms. It can't be 2 sigma bonds. So now we can just look at, if we know that this is a sigma and a pi together in the double bond, we can just add up the sigmas. 1, 2, 3 for this carbon, and the same for this carbon. 1, 2, 3. So we would say have to have 3 hybrid orbitals because we have 3 sigma bonds. Thus we have to have each carbon being sp2, 1s, the 2s, and the 2 of the 2 p's. Put into the meat grinder, we'd get 3 hybrid orbitals. 3 sp2 hybrid orbitals. These are, again, still atomic orbitals that are going to be used for bonding. That's one way to set the hybridization for these 2 carbons as sp2. Sorry, superscript, not subscript. The better way, I think, the faster way, is just to say, what number of pi bonds do we have off the carbon? Well, this was a sigma, singles are sigmas, but double was a sigma and a pi together. So we have 1 pi off of each carbon. 1 pi bond, off of each carbon. Well, to make a pi bond, and I'm just going to show it from the side view, we have to use p orbitals that are overlapping side by side. So the p orbitals are not head to head, but they're side to side. So this has to have a p orbital. And so also does the other carbon. And we leave that out of the meat grinder. See, I've circled only the 2s and 2 of the 2 p's. We've left 1 out of the meat grinder so that we can make that pi bond that's denoted in the double bond we have shown here. So that can be a simpler rule, I hope, a better rule. 1 pi bond atom is sp2 hybridized. Why? Because we need 1 p orbital. You kind of just, like when you have pi bond, you say, oh, that's made up of a p orbital overlapping with a p orbital. Just take the I out. A pi bond involves a p orbital. So we had to take, instead of using 3, we had to take 1 out and only use 2. So that's a good rule to use, maybe a better rule. And let's just now jump from that setting of hybridization to the orbital picture. The three hybrid orbitals are at maximum separation to each other, and they're sort of shown here in green. Just going to kind of circle to maybe denote the position. It's a trigonal planar. This is coming out in the 120 degree angle to this hybrid orbital, which is 120 degrees oriented to this hybrid orbital, but they're all three in a plane, and normal to that plane is our, in sort of a turquoise blue here, is our p orbital. This is a side view, and we're looking straight down the p orbital, and we can see the 120 degree orientation of the hybrid orbitals. So that's the picture of sp2 hybridization for these two carbons. Let's bring the two carbons together in a bond. These two carbons, we're just kind of showing these two carbons as sp2 hybridized, and we're going to push them together into a valence bond description and leave out the hydrogens like we did in the last one. So the two carbons come together and we get a sigma bond, of course, and we get a pi bond. You see the two p orbitals are overlapping side by side, and of course we have not shown the hydrogens. That's just a view we want to have our eye go to when we see lines and letters. We want our eye to be seeing orbitals. You say, how do I see the pure orbitals behind the letters and lines? Well, just kind of make note of its hybridization. We said again, these two carbons, because they each have one pi bond off of them, are sp2 hybridized. Well, we know then that the hydrogens here, being on the wedge and the dash, coming out towards us and into the back, are going to be 120 degrees oriented to each other because they're bonded through single bonds using the hybrid orbital of this carbon. And the carbon to this carbon has a sigma bond, which is going to be then putting this carbon at a 120 degree angle to this hydrogen, which is a 120 degree angle to this hydrogen. And so if this is to the back and this is to the front, we're really looking at a side view of the pi bonding. It would be above and below the plane that's created by the four hydrogens in the carbon. So it would be a side view, just kind of as it's shown here. Not a top view, because not a top view of that p orbital where we have the other. We would not be looking at a top view of the p orbitals because we know the hydrogens are bonded using, this is the hybrid orbitals, this being the p orbitals. We're not looking at a top view down the p orbital because we see the hydrogens are on the wedge and the dash. So we are looking at a side view, just as it's shown here. That's our, oh, sorry, and I didn't just put this in here. You cannot have rotational motion about a pi bond. You can't rotate this carbon while you hold this one fast. That's just not allowed with pi bonding. We do not have, as we do with sigma bonding, rotation about pi bonding like we have rotation about sigma bonding. This is our last of the three, and then we'll finish with nitrogens and oxygens. So let's look at our last structure that has two carbons and only two hydrogens. This would be the molecular formula, and there's only one way to satisfy that molecular formula, C2H2, to have the two hydrogens on each end of the carbon-carbon triple bond. So how do we set the hybridization for these carbons? Well, again, a good rule is if there are two sigma bonds off the carbon, we would say it's sp hybridized because we need two hybrid orbitals. But a better way is just to say this carbon has two pi bonds off it, and so also does this. So each carbon needs to have two p orbitals left out of two p orbitals, plural there, s, out of the hybridization process. So we're leaving these out. They're represented here. We're mixing just two orbitals, the 2s and the 2p, to get two hybrid orbitals, s2, sp hybrid orbitals. And these go into bonding with the hydrogen and with the carbon through a sigma bond. So that's how we can set these quickly. If we just count the pi bonds, they have two. We have to keep two out, so we're not a 3, not a 2, but we just 1. You don't mark it if it's just 1, it's just sp hybridized. So these two carbons are sp hybridized. Now let's use that to set the picture of the structure acetylene, or this is also called ethyne. So we just simply say, and this is going to be a little bit hard to see, but we have a axis here, PZ we'll call it, and that's going to overlap with the PZ, the 2p orbital, the 2pz, and these are side by side. And we also have, it's hard to see here, the purple and the yellow, let's say py, can overlap with this py. So we have side to side overlap of the 2p orbitals on each carbon to give 2 pi bonds. And of course the orange on orange gives us the sigma bond. And that's, again, developing from the lines and letters an orbital picture of the structure. And here we are showing the hydrogens. So this is a valence bond description of acetylene. It gets a little bit easier as you take time and develop this skill of seeing past letters and lines through the hybridization you set. We set these on the last slide to SP, to using that as a doorway to see an orbital picture of the structure. Let's finish with the last 2 slides on oxygens and nitrogens. They're a little harder because oxygens and nitrogens don't have 4 bonds off of them. So oxygen has just 2. So what we have to look at is 2 considerations. Either it's maximum separation that lowers the energy of the structure, or resonance. So really we're going to be pitting these 2 against each other, and if you have to pick one as lowering the energy of the structure, always go with resonance. Maximum separation is trumped by resonance, and we're going to use, or in the next presentation we're going to introduce resonance. So let's figure out what we mean about setting the hybridization by maximum separation. All we mean is this: take all pairs, bonding or non-bonding, and set them to maximum, distances from each other through the hybridization. Well, to do that, we would set this one as sp3, and so also we would set this one to sp3, because that would maximize the separation of bonding and non-bonding pairs. We can do the same thing for a carbanion. It doesn't matter if it's charged. It doesn't change the setting of hybridization. We still have a non-bonding pair and 3 bonding pairs, so this also would be sp3 hybridized. Now, borane, BH3, there are only 3 bonding pairs off of boron. There are no other electrons. So to maximize the separation, we'd say sp2. We can do the same thing for a carbocation that has just 3 hydrogens off of it. It would be sp2. Now again, what's more important than just setting hybridization is seeing the orbital picture through the hybridization. So if this carbon is sp2, because there are only bonding pairs off of it to 3 hydrogens, there are no other electrons, we could say we have an empty p orbital, and it would be perpendicular to the plane of these 3 hydrogens. So maybe these are a little bit, should be really, to be more accurate, we could say, if we're really wanting to sort of demonstrate the plane, we're going to say these are really kind of close to each other, because this is straight out and this is straight back, but we're just offsetting them a little bit so we can draw the 2 hydrogens. So this would be a side view of the p orbital. We would know it would be right here because we know these are in a trigonal planar arrangement. Alright, so that's it. We'll move into resonance setting hybridization in the next presentation. Let's remember some general rules. 4 single bonds off of an atom. The atom is sp3 hybridized. 1 pi bond, it's sp2, because we need to keep 1 p orbital out to make the 1 pi bond. If we have 2 pi bonds, well then we don't take but 1 p orbital into the mix, because we need to keep 2 out if we have 2 pi bonds. So just sp hybridization. These are just great, quick general rules that'll work for setting hybridization for most, again, carbons, nitrogens, and oxygens. Charge doesn't matter. When more than one hybridization is possible, go with the one that lowers the energy of the structure. For now, we're just considering maximum separation. In the next presentation, we'll consider resonance. And when do you really have to consider it? Well, here's the most important, rule of these 2, or I don't know if it's a more important one, but it really sets this first one. Not all N's and O's in single bonds are sp3 hybridized. A lot of students want to go there. when these N's and O's with lone pairs are next to a pi bond, not in a pi bond, but next to a pi bond, they're going to be considered to be sp2 hybridized. It's going to be because of resonance. And because of that, when those N's or O's are next to a pi bond, they're often partially positive. So the rule that most students want to go by is that all N's and O's are partially negative. That is not true. Not all N's and O's are partially negative. People want to just go with a simple rule, N's and O's are more electronegative, they're always partially negative, therefore. No, it's not always true that N's and O's are partially negative. So if we look at aspirin here, by our rules we know this O is sp2, it's in one pi bond. So also are these 6 carbons, they're sp2 because they're all in, each carbon here has one pi bond off of it. This O would be sp2 hybridized because it has one pi bond off of it. This pendant methyl group, CH3 group, would be sp3 hybridized because it has 4 single bonds off of it. Signals have to be sigmas, and sigmas are made using hybrid orbitals. We have need of 4 of them, sp3. Hybridization gets us there. On the next presentation, we're going to see that these 2 oxygens here are not sp3. They're not partially negative. They're sp2, and say it ain't so, partially positive. We'll have a great, time absorbing this, and we'll see you in the 4th presentation.